Cassini-Huygens is an unmanned spacecraft sent to the planet Saturn. It is a flagship-class NASA-ESA-ASI robotic spacecraft sent to the Saturn system. It has studied the planet and its many natural satellites since arriving there in 2004, also observing Jupiter, the heliosphere, and testing the theory of relativity. Launched in 1997 after nearly 2 decades of development, it includes a Saturn orbiter and an atmospheric probe lander for the moon Titan called Huygens, which entered and landed on Titan in 2005. Cassini is the 4th space probe to visit Saturn and the first to enter orbit, and its mission is ongoing as of 2014. The 2-part spacecraft is named after astronomers Giovanni Cassini and Christiaan Huygens. The spacecraft launched on October 15, 1997 aboard a Titan IVB Centaur and entered orbit around Saturn on July 1, 2004, after an interplanetary voyage which included flybys of Earth, Venus, and Jupiter. On December 25, 2004, Huygens separated from the orbiter at approximately 0200 UTC. It reached Saturn's moon Titan on January 14, 2005, when it entered Titan's atmosphere and descended to the surface. It successfully returned data to Earth, using the orbiter as a relay. This was the first landing ever accomplished in the outer solar system. Nearly a decade after entering orbit, on April 3, 2014, NASA reported that evidence for a large underground ocean of liquid water on Enceladus, a moon of Saturn, had been found by Cassini. According to scientists, evidence of an underground ocean suggests that Enceladus is one of the most likely places in the solar system to host microbial life. On June 30, 2014, NASA celebrated 10 years of Cassini exploring Saturn and its moons, highlighting the discovery of water activity on Enceladus among other findings. Overview: 16 European countries and the United States make up the team responsible for designing, building, flying and collecting data from the Cassini orbiter and Huygens probe. The mission is managed by NASA unregistered trademark S-Jet Propulsion Laboratory in the United States, where the orbiter was assembled. Huygens was developed by the European Space Research and Technology Centre. The centre's prime contractor, or copyright Rospatiel of France, assembled the probe with equipment and instruments supplied by many European countries. The Italian Space Agency provided the Cassini orbiter's high-gain radio antenna, with the incorporation of a low-gain antenna, a compact and lightweight radar, which also uses the high-gain antenna and serves as a synthetic aperture radar, a radar altimeter, a radiometer, the radioscience subsystem, the visible channel portion VIMS via VIMS spectrometer. On April 16, 2008, NASA announced a 2-year extension of the funding for ground operations of this mission, at which point it was renamed to the Cassini Equinox mission. This was again extended in February 2010 with the Cassini Solstice mission. Naming: it consists of 2 main elements, the ASI NASA Cassini orbiter, named for the Italian-French astronomer Giovanni Domenico Cassini, and the ESA-developed Huygens probe, named for the Dutch astronomer, mathematician and physicist Christiaan Huygens. Huygens discovered Titan, and Cassini discovered a few more of Saturn's moons. The mission was commonly called Saturn Orbiter Titan Probe during gestation, both as a Mariner Mark II mission and generically. Cassini-Huygens is a flagship-class mission to the outer planets. The other planetary flagships include Galileo, Voyager, and Viking. Objectives: Cassini has 7 primary objectives: determine the 3-dimensional structure and dynamic behavior of the rings of Saturn, determine the composition of the satellite surfaces and the geological history of each object, determine the nature and origin of the dark material on Iapetus's leading hemisphere, measure the 3-dimensional structure and dynamic behavior of the magnetosphere, study the dynamic behavior of Saturn's atmosphere at cloud level, study the time variability of Titan's clouds and hazes, characterize Titan's surface on a regional scale. Cassini-Huygens was launched on October 15, 1997, from Cape Canaveral Air Force Station Space Launch Complex F-40 using a U.S. Air Force Titan IVB Centaur rocket. The complete launcher was made up of a 2-stage Titan IV booster rocket, 2 strap-on solid rocket motors, the Centaur upper stage, and a payload enclosure, or fairing. The total cost of this scientific exploration mission is about $3.26 a billion, including $1.4 billion for pre-launch development, $704 million for mission operations, $54 a million for tracking and $422 a million for the launch vehicle. The United States contributed $2.6 a billion, the ESA $500 a million, and the ASI $160 a million. The primary mission for Cassini was completed on July 30, 2008. The mission was extended to June 2010. This studied the Saturn system in detail during the planet's equinox, which happened in August 2009. On February 3, 2010, NASA announced another extension for Cassini, lasting 6.5 years until 2017, ending at the time of summer solstice in Saturn's northern hemisphere. The extension enables another 155 revolutions around the planet, 54 flybys of Titan and 11 flybys of Enceladus. In 2017, an encounter with Titan will change its orbit in such a way that, at closest approach to Saturn, it will be only 3,000 km above the planet's cloud tops, below the inner edge of the D-ring. This sequence of proximal orbits will end when another encounter with Titan sends the probe into Saturn's atmosphere. Itinerary. History. Cassini-Huygens' origins date to 1982, when the European Science Foundation and the American National Academy of Sciences formed a working group to investigate future cooperative missions. Two European scientists suggested a paired Saturn orbiter and Titan probe as a possible joint mission. In 1983, NASA's Solar System Exploration Committee recommended the same orbiter and probe pair as a core NASA project. NASA and the European Space Agency performed a joint study of the potential mission from 1984 to 1985. ESA continued with its own study in 1986, while the American astronaut Sally Ride, in her influential 1987 report NASA Leadership and America's Future in Space, also examined and approved of the Cassini mission. While Ride's report described the Saturn orbiter and probe as a NASA solo mission, in 1988 the Associate Administrator for Space Science and Applications of NASA Len Fisk returned to the idea of a joint NASA and ESA mission. He wrote to his counterpart at ESA, Roger Bonnet, strongly suggesting that ESA choose the Cassini mission from the three candidates at hand and promising that NASA would commit to the mission as soon as ESA did. At the time, NASA was becoming more sensitive to the strain that had developed between the American and European space programs as a result of European perceptions that NASA had not treated it like an equal during previous collaborations. NASA officials and advisors involved in promoting and planning Cassini-Huygens attempted to correct this trend by stressing their desire to evenly share any scientific and technology benefits resulting from the mission. In part, this newfound spirit of cooperation with Europe was driven by a sense of competition with the Soviet Union, which had begun to cooperate more closely with Europe as ESA drew further away from NASA. The collaboration not only improved relations between the two space programs but also helped Cassini-Huygens survive congressional budget cuts in the United States. Cassini-Huygens came under fire politically in both 1992 and 1994, but NASA successfully persuaded the U.S. Congress that it would be unwise to halt the project after ESA had already poured funds into development because frustration on broken space exploration promises might spill over into other areas of foreign relations. The project proceeded politically smoothly after 1994, although citizens groups concerned about its potential environmental impact attempted to derail it through protests and lawsuits until and past its 1997 launch. Spacecraft design. The spacecraft was planned to be the second three-axis stabilized, RTG-powered Mariner Mark II, a class of spacecraft developed for missions beyond the orbit of Mars. Cassini was developed simultaneously with the Comet Rendezvous asteroid Flyby spacecraft, but budget cuts and project rescopings forced NASA to terminate CRAF development to save Cassini. As a result, Cassini became more specialized. The Mariner Mark II series was cancelled. Including the orbiter and probe, It is the largest and most complex unmanned interplanetary spacecraft built. The orbiter has a mass of 2,150 kg, the probe 350 kg. With the launch vehicle adapter and 3,132 kg of propellants at launch, the spacecraft had a mass of 5,600 kg. Only the two Phobos spacecraft sent to Mars by the Soviet Union were heavier. The Cassini spacecraft is 6.8 meters high and 4 meters wide. Spacecraft complexity is increased by its trajectory to Saturn, and by the ambitious science at its destination. Cassini has 1,630 interconnected electronic components, 22,000 wire connections, and 14 kilometers of cabling. The core control computer CPU is a redundant MILS TD1758 control system. Cassini is powered by 32.7 kg of plutonium-238 The heat from the material's radioactive decay is turned into electricity. Huygens was supported by Cassini during cruise, but used chemical batteries when independent. Now the Cassini probe is orbiting Saturn. It is between 8.2 and 10.2 astronomical units from the Earth. It takes 68 to 84 minutes for radio signals to travel from Earth to the spacecraft, and vice versa. Thus ground controllers cannot give real-time instructions for daily operations or for unexpected events. Even if response was immediate, at least 2 hours pass between the occurrence of a problem and the reception of the engineer's response by the satellite. Instruments. Cassini's instrumentation consists of a synthetic aperture radar mapper, a charge-coupled device imaging system, a visible infrared mapping spectrometer, a composite infrared spectrometer, a cosmic dust analyzer, a radio and plasma wave experiment, a plasma spectrometer, an ultraviolet imaging spectrograph, a magnetospheric imaging instrument, a magnetometer and an ion-neutral mass spectrometer. Telemetry from the communications antenna and other special transmitters will also be used to make observations of the atmospheres of Titan and Saturn and to measure the gravity fields of the planet and its satellites. Cassini Plasma Spectrometer. The CAPS is a direct sensing instrument that measures the energy and electrical charge of particles that the instrument encounters. CAPS will measure the molecules originating from Saturn's ionosphere and also determine the configuration of Saturn's magnetic field. CAPS will also investigate plasma in these areas as well as the solar wind within Saturn's magnetosphere. CAPS has been turned off since June 2011 because of an electrical short circuit that occurred in the instrument. The instrument was powered on in March 2012. After 78 days a second short circuit forced the instrument to be shut down again. Cosmic Dust Analyzer. The CDA is a direct sensing instrument that measures the size, speed, and direction of tiny dust grains near Saturn. Some of these particles are orbiting Saturn, while others may come from other star systems. The CDA on the orbiter is designed to learn more about these mysterious particles, the materials in other celestial bodies and potentially about the origins of the universe. Composite infrared spectrometer. The CIRCLES is a remote sensing instrument that measures the infrared waves coming from objects to learn about their temperatures, thermal properties, and compositions. Throughout the Cassini-Huygens mission, the CIRS will measure infrared emissions from atmospheres, rings and surfaces in the vast Saturn system. It will map the atmosphere of Saturn in 3 dimensions to determine temperature and pressure profiles with altitude, gas composition, and the distribution of aerosols and clouds. It will also measure thermal characteristics and the composition of satellite surfaces and rings. Ion and neutral mass spectrometer. The INMS is a direct sensing instrument that analyzes charged particles and neutral particles near Titan and Saturn to learn more about their atmospheres. INMS is intended also to measure the positive ion and neutral environments of Saturn's icy satellites and rings. Imaging Science Subsystem. The ISLANS is a remote sensing instrument that captures most images in visible light, and also some infrared images and ultraviolet images. The ISLANS has taken hundreds of thousands of images of Saturn, its rings, and its moons, for return to the Earth by radio telemetry. The ISLANS has a wide-angle camera that takes pictures of large areas, and a narrow-angle camera that takes pictures of small areas in fine detail. Each of these cameras uses a sensitive charge-coupled device as its electromagnetic wave detector. Each CCD has a 1024 square array of pixels, 12 AI 1/4 m on a side. Both cameras allow for many data collection modes, including on-chip data compression. Both cameras are fitted with spectral filters that rotate on a wheel to view different bands within the electromagnetic spectrum ranging from 0.2 to 1.1 AI 1/4 m. Dual technique magnetometer. The MAG is a direct sensing instrument that measures the strength and direction of the magnetic field around Saturn. The magnetic fields are generated partly by the intensely hot molten core at Saturn's center. Measuring the magnetic field is one of the ways to probe the core, even though it is far too hot and deep to visit. MAG aims to develop a three-dimensional model of Saturn's magnetosphere, and determine the magnetic state of Titan and its atmosphere, and the icy satellites and their role in the magnetosphere of Saturn. Magnetospheric imaging instrument. The MIMI is both a direct and remote sensing instrument that produces images and other data about the particles trapped in Saturn's huge magnetic field, or magnetosphere. This information will be used to study the overall configuration and dynamics of the magnetosphere and its interactions with the solar wind, Saturn's atmosphere, Titan, rings, and icy satellites. MIMI includes the ion and neutral camera, which captures and measures energetic neutral atoms. Radar. Then-board radar is a remote active and remote passive sensing instrument that will produce maps of Titan's surface. It measures the height of surface objects by sending radio signals that bounce off Titan's surface and timing their return. Radio waves can penetrate the thick veil of haze surrounding Titan. The radar will listen for radio waves that Saturn or its moons may be producing. Radio and plasma wave science instrument. The RPWS is a direct and remote sensing instrument that receives and measures radio signals coming from Saturn, including the radio waves given off by the interaction of the solar wind with Saturn and Titan. RPWS is to measure the electric and magnetic wave fields in the interplanetary medium and planetary magnetospheres. It will also determine the electron density and temperature near Titan and in some regions of Saturn's magnetosphere. RPWS studies the configuration of Saturn's magnetic field and its relationship to Saturn kilometric radiation, as well as monitoring and mapping Saturn's ionosphere, plasma, and lightning from Saturn's atmosphere. Radio Science Subsystem. The RSS is a remote sensing instrument that uses radio antennas on Earth to observe the way radio signals from the spacecraft change as they are sent through objects, such as Titan's atmosphere or Saturn's rings, or even behind the Sun. The RSS also studies the compositions, pressures and temperatures of atmospheres and ionospheres, radial structure and particle size distribution within rings, body and system masses and gravitational waves. The instrument uses the spacecraft X-band communication link as well as S-band downlink and Ka-band uplink and downlink. Ultraviolet imaging spectrograph. The UVIS is a remote sensing instrument that captures images of the ultraviolet light reflected off an object, such as the clouds of Saturn and/or its rings, to learn more about their structure and composition. Designed to measure ultraviolet light over wavelengths from 55.8 to 190 nm, this instrument is also a valuable tool to help determine the composition, distribution, aerosol particle content and temperatures of their atmospheres. Unlike other types of spectrometer, this sensitive instrument can take both spectral and spatial readings. It is particularly adept at determining the composition of gases. Spatial observations take a wide by narrow view, only 1 pixel tall and 64 pixels across. The spectral dimension is 1024 pixels per spatial pixel. Also, it can take many images that create movies of the ways in which this material is moved around by other forces. Visible and infrared mapping spectrometer. The VIMS is a remote sensing instrument that captures images using visible and infrared light to learn more about the composition of moon surfaces, the rings, and the atmospheres of Saturn and Titan. It is made up of 2 cameras in one used to measure visible light, the other infrared. VIMS measures reflected and emitted radiation from atmospheres, rings and surfaces over wavelengths from 350 to 5100 nm, to help determine their compositions, temperatures and structures. It also observes the sunlight and starlight that passes through the rings to learn more about their structure. Scientists plan to use VIMS for long-term studies of cloud movement and morphology in the Saturn system, to determine Saturn's weather patterns. Plutonium power source. Because of Saturn's distance from the Sun, solar arrays were not feasible as power sources for this space probe. To generate enough power, such arrays would have been too large and too heavy. Instead, the Cassini orbiter is powered by 3 radioisotope thermoelectric generators, which use heat from the natural decay of about 33 kg of plutonium-238 to generate direct current electricity via thermoelectrics. The RTGs on the Cassini mission have the same design as those used on the New Horizons, Galileo, and Ulysses space probes, and they were designed to have very long operational lifetimes. At the end of the nominal 11-year Cassini mission, they will still be able to produce 600 to 700 watts of electrical power. To gain momentum while already in flight, the trajectory of the Cassini mission included several gravitational slingshot maneuvers, 2 flyby passes of Venus, 1 more of the Earth, and then 1 of the planet Jupiter. The terrestrial flyby was the final instance when the Cassini space probe posed any conceivable danger to human beings. The maneuver was successful, with Cassini passing by 1,171 km above the Earth on August 18, 1999. Had there been any malfunction causing the Cassini space probe to collide with the Earth, NASA's Complete Environmental Impact Study estimated that, in the worst case, a significant fraction of the 33 kg of plutonium-238 inside the RTGs would have been dispersed into the Earth's atmosphere so that up to 5 billion people could have been exposed, causing up to an estimated 5,000 additional cancer deaths, but the odds against that happening were more than 1 million to 1. Telemetry. The Cassini spacecraft is capable of transmitting several different telemetry formats. The telemetry subsystem is perhaps the most important subsystem, because without it there could be no data return. Cassini's telemetry was developed from ground up, due to the spacecraft using a more modern set of computers than previous missions. 1. Therefore, Cassini was the first spacecraft to adopt many packets to reduce the complexity of the telemetry dictionary, and the software development process led to the creation of a telemetry manager for the mission. There are currently around 1088 channels assembled in the Cassini telemetry dictionary. Out of these 67 lower complexity mini-packets, some 6 mini-packets contained the subsystem covariance and Kalman gain elements, not used during normal mission operations. This left 947 measurements in 61 mini-packets. A total of 7 telemetry maps corresponding to 7 AACS telemetry modes were constructed. These modes are, record, nominal cruise, medium-slow cruise, slow cruise, orbital ops, ARF, ATE calibration. These 7 maps cover all spacecraft telemetry modes. Huygens probe. The Huygens probe, supplied by the European Space Agency and named after the 17th-century Dutch astronomer who first discovered Titan, Christiaan Huygens, scrutinized the clouds, atmosphere, and surface of Saturn's moon Titan in its descent on January 15, 2005. It was designed to enter and break in Titan's atmosphere and parachute a fully instrumented robotic laboratory down to the surface. The probe system consisted of the probe itself which descended to Titan, and the probe support equipment which remained attached to the orbiting spacecraft. The PSE includes electronics that track the probe, recover the data gathered during its descent, and process and deliver the data to the orbiter that transmits it to Earth. The core control computer CPU is a redundant MILS TD1750A control system. The data was transmitted by a radio link between Huygens and Cassini provided by Probe Data Relay Subsystem. As the probe's mission could not be telecommanded from Earth because of the great distance, it was automatically managed by the Command Data Management Subsystem. The PDRS and CDMS were provided by the Italian Space Agency. Selected events and discoveries. Venus and Earth flybys and the cruise to Jupiter. the Cassini space probe performed 2 gravitational assist flybys of Venus on April 26, 1998, and June 24, 1999. These flybys provided the space probe with enough momentum to travel all the way out to the asteroid belt. At that point, the Sun's gravity pulled the space probe back into the inner solar system, where it made a gravitational assist flyby of the Earth. On August 18, 1999, at 3:28 UTC, the Cassini craft made a gravitational assist flyby of the Earth. 1 hour and 20 minutes before closest approach, Cassini made its closest approach to the Earth's moon at 377,000 kilometers, and it took a series of calibration photos. On January 23, 2000, the Cassini space probe performed a flyby of the asteroid 2685 Marsersky at around 10:00 UTC. The Cassini craft took photos in the period 5 to 7 hours before the flyby at a distance of 1.6 million kilometers, and a diameter of 15 to 20 km was estimated for the asteroid. Jupiter flyby. Cassini made its closest approach to Jupiter on December 30, 2000, and made many scientific measurements. About 26,000 images of Jupiter were taken during the months-long flyby. It produced the most detailed global color portrait of Jupiter yet, in which the smallest visible features are approximately 60 km across. The New Horizons mission to Pluto captured more recent images of Jupiter, with a closest approach on February 28, 2007. A major finding of the flyby, announced on March 6, 2003, was of Jupiter's atmospheric circulation. Dark belts alternate with light zones in the atmosphere, and scientists had long considered the zones, with their pale clouds, to be areas of upwelling air, partly because many clouds on Earth form where air is rising. But analysis of Cassini imagery showed that individual storm cells of upwelling bright white clouds too small to see from Earth, pop up almost without exception in the dark belts. According to Anthony Del Genio of NASA's Goddard Institute for Space Studies, the belts must be the areas of net rising atmospheric motion on Jupiter, so the net motion in the zones has to be sinking. Other atmospheric observations included a swirling dark oval of high atmospheric haze, about the size of the Great Red Spot, near Jupiter's North Pole. Infrared imagery revealed aspects of circulation near the poles, with bands of globe-encircling winds, with adjacent bands moving in opposite directions. The same announcement also discussed the nature of Jupiter's rings. Light scattering by particles in the rings showed the particles were irregularly shaped and likely originate as ejecta from micrometeorite impacts on Jupiter's moons, probably Metis and Adrastea. Tests of general relativity. On October 10, 2003, the Cassini science team announced the results of tests of Einstein's general theory of relativity, which were done by using radio waves that were transmitted from the Cassini space probe. This is currently the best measurement of post-Newtonian parameter I cubed. The result I cubed equals 1 plus a, 10^5 agrees with the prediction of standard general relativity, I cubed equals 1. The radio scientists measured a frequency shift in the radio waves to and from the spacecraft, while those signals traveled close to the Sun according to the general theory of relativity. A massive object like the Sun causes space-time to curve, and a beam of radio waves that passes by the Sun has to travel farther because of the curvature. The extra distance that the radio waves traveled from the Cassini craft, past the Sun, to the Earth delays their arrival. The amount of this time delay provides a sensitive test of the calculated predictions of Einstein's relativity theory. Although some measurable deviations from the values that are calculated using the general theory of relativity are predicted by some unusual cosmological models, no deviations of this type were found by this experiment. Previous tests using radio waves that were transmitted by the Viking and Voyager space probes were in agreement with the calculated values from general relativity to within an accuracy of 1 part in 1,000. The more refined measurements from the Cassini space probe experiment improved this accuracy to about 1 part in 51,000, with the measured data firmly supporting Einstein's general theory of relativity. New moons of Saturn. Using images taken by Cassini, 3 new moons of Saturn were discovered in 2004. They are very small and were given the provisional names S/2004-ASI-1, S/2004-ASI-2 and S/2004-ASI-5 before being named Methane, Palin and Polydeuces at the beginning of 2005. On May 1, 2005, a new moon was discovered by Cassini in the Keeler Gap. It was given the designation S/2005-ASI-1 before being named Daphnis. The only other then-known moon inside Saturn's ring system is Pan. A fifth new moon was discovered by Cassini on May 30, 2007, and was provisionally labeled S/2007-S4. It is now known as Anth. A press release on February 3, 2009 showed a sixth new moon found by Cassini. The moon is approximately 1/3 of a mile in diameter within the G-ring of the ring system of Saturn, and is now named Allegoian. A press release on November 2, 2009 mentions the seventh new moon found by Cassini on July 26, 2009. It is presently labeled S/2009-S1 and is approximately 300 am in diameter in the B-ring system. On April 14, 2014, NASA scientists reported the possible beginning of a new moon, within the A-ring, of the planet Saturn. Phoebe flyby. On June 11, 2004, Cassini flew by the moon Phoebe. This was the first opportunity for close-up studies of this moon since the Voyager 2 flyby. It also was Cassini's only possible flyby for Phoebe due to the mechanics of the available orbits around Saturn. First close-up images were received on June 12, 2004, and mission scientists immediately realized that the surface of Phoebe looks different from asteroids visited by spacecraft. Parts of the heavily cratered surfaces look very bright in those pictures, and it is currently believed that a large amount of water ice exists under its immediate surface. Saturn rotation. In an announcement on June 28, 2004, Cassini program scientists described the measurement of the rotational period of Saturn. Since there are no fixed features on the surface that can be used to obtain this period, the repetition of radio emissions was used. These new data agree with the latest values measured from Earth, and constitute a puzzle to the scientists. It turns out that the radio rotational period has changed since it was first measured in 1980 by Voyager, and that it is now 6 minutes longer. This does not indicate a change in the overall spin of the planet, but is thought to be due to movement of the source of the radio emissions to a different latitude, at which the rotation rate is different. Orbiting Saturn. On July 1, 2004, the spacecraft flew through the gap between the F and G rings and achieved orbit, after a 7-year voyage. It is the first spacecraft to ever orbit Saturn. The Saturn orbital insertion maneuver performed by Cassini was complex, requiring the craft to orient its high-gain antenna away from Earth and along its flight path, to shield its instruments from particles in Saturn's rings. Once the craft crossed the ring plane, it had to rotate again to point its engine along its flight path, and then the engine fired to decelerate the craft by 622 meters per second to allow Saturn to capture it. Cassini was captured by Saturn's gravity at around 8:54 p.m. Pacific Daylight Time on June 30, 2004. During the maneuver, Cassini passed within 20,000 km of Saturn's crowd tops. Although it is in Saturn orbit, departure from the Saturn system was evaluated in 2008 during end-of-mission planning. Titan flybys. Cassini had its first distant flyby of Saturn's largest moon, Titan, on July 2, 2004, only a day after orbit insertion, when it approached to within 339,000 km of Titan and provided the best look at the Moon's surface to date. Images taken through special filters showed south polar clouds thought to be composed of methane and surface features with widely differing brightness. On October 27, 2004, the spacecraft executed the first of the 45 planned close flybys of Titan when it flew a mere 1,200 kilometers above the Moon. Almost 4 gigabits of data were collected and transmitted to Earth, including the first radar images of the Moon's haze-enshrouded surface. It revealed the surface of Titan to be relatively level, with topography reaching no more than about 50 meters in altitude. The flyby provided a remarkable increase in imaging resolution over previous coverage. Images with up to 100 times better resolution were taken and are typical of resolutions planned for subsequent Titan flybys. Huygens lands on Titan. Cassini released the Huygens probe on December 25, 2004, by means of a spring and spiral rails intended to rotate the probe for greater stability. It entered the atmosphere of Titan on January 14, 2005, and after a 2.5-hour descent landed on solid ground. Although Cassini successfully relayed 350 of the pictures that it received from Huygens of its descent and landing site, a software error failed to turn on one of the Cassini receivers and caused the loss of the other 350 pictures. Enceladus flybys. During the first two close flybys of the Moon Enceladus in 2005, Cassini discovered a deflection in the local magnetic field that is characteristic for the existence of a thin but significant atmosphere. Other measurements obtained at that time point to ionized water vapor as being its main constituent. Cassini also observed water ice geysers erupting from the south pole of Enceladus, which gives more credibility to the idea that Enceladus is supplying the particles of Saturn's E-ring. Mission scientists began to suspect that there may be pockets of liquid water near the surface of the Moon that fuel the eruptions. On March 12, 2008, Cassini made a close flyby of Enceladus, getting within 50 km of the Moon's surface. The spacecraft passed through the plumes extending from its southern geysers, detecting water, carbon dioxide and various hydrocarbons with its mass spectrometer, while also mapping surface features that are at much higher temperature than their surroundings with the infrared spectrometer. Cassini was unable to collect data with its cosmic dust analyzer due to an unknown software malfunction. On November 21, 2009, Cassini made its eighth flyby of Enceladus, this time with a different geometry and approaching within 1,600 kilometers of the surface. The composite infrared spectrograph instrument produced a map of thermal emissions from the Baghdad-Sulcus Tiger Stripe. The data returned helped create a detailed and high-resolution mosaic image of the southern part of the Moon's Saturn-facing hemisphere. On April 3, 2014, NASA reported evidence of a large salty internal ocean of liquid water in Enceladus. The presence of an internal salty ocean in contact with the Moon's rocky core places Enceladus among the most likely places in the Solar System to host alien microbial life. Radio occultations of Saturn's rings. In May 2005, Cassini began a series of radio occultation experiments to measure the size distribution of particles in Saturn's rings, and measure the atmosphere of Saturn itself. For over 4 months, Cassini completed orbits designed for this purpose. During these experiments, Cassini flew behind the ring plane of Saturn, as seen from Earth, and transmitted radio waves through the particles. The radio signals were received on Earth, where the frequency, phase, and power of the signal was analyzed to help determine the structure of the rings. Spoke phenomenon verified. In images captured September 5, 2005, Cassini detected spokes in Saturn's rings, previously seen only by the visual observer Stephen James O'Meara in 1977 and then confirmed by the Voyager space probes in the early 1980s. Lakes of Titan. Radar images obtained on July 21, 2006 appear to show lakes of liquid hydrocarbon in Titan's northern latitudes. This is the first discovery of currently existing lakes anywhere besides Earth. The lakes range in size from 1 to 100 kilometers across. On March 13, 2007, the Jet Propulsion Laboratory announced that it found strong evidence of seas of methane and ethane in the northern hemisphere of Titan. At least one of these is larger than any of the Great Lakes in North America. Saturn hurricane. In November 2006, scientists discovered a storm at the south pole of Saturn with a distinct eye wall. This is characteristic of a hurricane on Earth and had never been seen on another planet before. Unlike a terrestrial hurricane, the storm appears to be stationary at the pole. The storm is 8,000 kilometers across, and 70 kilometers high, with winds blowing at 560 kilometers per hour. Iapetus flyby. On September 10, 2007, Cassini completed its flyby of the strange, two-toned, walnut-shaped moon, Iapetus. Images were taken from 1,000 miles above the surface. As it was sending the images back to Earth, it was hit by a cosmic ray which forced it to temporarily enter safe mode. All of the data from the flyby was recovered. Mission extension. On April 15, 2008, Cassini received funding for a 2-year extended mission. It consisted of 60 more orbits of Saturn, with 21 more close Titan flybys, 7 of Enceladus, 6 of Mimas, 8 of Tethys, and 1 targeted flyby each of Dione, Rhea, and Helene. The extended mission began on July 1, 2008, and was renamed the Cassini Equinox mission as the mission coincided with Saturn's equinox. A proposal was submitted to NASA for a second mission extension, provisionally named the Extended Mission or XXM. This was subsequently approved and renamed the Cassini Solstice mission. It includes Cassini orbiting Saturn 155 more times, conducting 54 additional flybys of Titan and 11 more of Enceladus. The chosen mission ending involves a series of close Saturn passes, approaching within the rings, then an entry into the Saturn atmosphere during the 2017 northern summer solstice, to destroy the spacecraft. Great Storm of 2010 and aftermath. On October 25, 2012, Cassini witnessed the aftermath of the massive Great White Spot Storm that recurs roughly every 30 years on Saturn. Data from Cassini's composite infrared spectrometer instrument indicated a powerful discharge from the storm that caused a temperature spike in the stratosphere of Saturn 83 Kelvin above normal. Simultaneously, a huge increase in ethylene gas was detected by NASA researchers at Goddard Research Center in Greenbelt, Maryland. Ethylene is a colorless and odorless gas that is highly uncommon on Saturn and is produced both naturally and through man-made sources on Earth. The storm that produced this discharge was first observed by Cassini on December 5, 2010 in Saturn's northern hemisphere. The storm is the first of its kind to be observed by a spacecraft in orbit around Saturn as well as the first to be observed at thermal infrared wavelengths, allowing scientists to observe the temperature of Saturn's atmosphere and track phenomena that are invisible to the naked eye. The spike of ethylene gas that was produced by the storm reached levels that were 100 times more than those thought possible for Saturn. Scientists have also determined that the storm witnessed was the largest, hottest stratospheric vortex ever detected in our solar system, initially being larger than Jupiter's Great Red Spot. Venus transit. On December 21, 2012, Cassini observed a transit of Venus across the Sun. The VIMS instrument analyzed sunlight passing through the Venusian atmosphere. VIMS previously observed the transit of exoplanet HD 189733b. The day the Earth smiled. On July 19, 2013, the probe was pointed towards Earth to capture an image of the Earth and the Moon, as part of a natural light, multi-image portrait of the entire Saturn system. The event was unique as it was the first time NASA informed the people of Earth that a long-distance photo was being taken in advance. The imaging team said they wanted people to smile and wave to the skies, with Cassini scientist, Carolyn Porco, describing the moment as a chance to celebrate life on the pale blue dot. Glossary. See also: Cassini Huygens timeline, Cassini Huygens retirement, Europlanet, Data Network, Galileo, Jupiter Orbiter and Entry Probe, Planetary Science Decadal Survey, Tom Crumages, References. Further reading, David M. Harland. Mission to Saturn, Cassini and the Huygens Probe. Springer Verlag. ISBN A1-85233-656-0. Ralph Lawrence and Jacqueline Mitten. Lifting Titan's Veil, Exploring the Giant Moon of Saturn. Cambridge University Press. ISBN A0-521-79348-3. Carl Grossman. The Wrong Stuff, The Space Program's Nuclear Threat to Our Planet. Common Courage Press. ISBN A1-56751-125-2. External links, official websites, Cassini-Huygens main page at NASA, Cassini mission homepage by the Jet Propulsion Laboratory, Cassini-Huygens mission profile by NASA's Solar System Exploration. telecommunications and imaging, Cassini imaging homepage, Descanso DSN telecom information, Cassi interactive web browser-based mission explorer simulator, Cassini information by the National Space Science Data Center. Photo gallery Euro full coverage, outside in a Euro film animated from hundreds of thousands of still Cassini photographs, around Saturn a Euro film featuring a virtual tour of Saturn made from a selection of more than 200,000 pictures snapped by Cassini from 2004 to 2012. Scientific press coverage, Cassini's Tour de Saturn Part A, B, C, D, E, FAR Euro descriptions of the 4-year tour of Saturn by Bruce Moman, Spaceflight Now news coverage of the mission, countdown to cancel the Cassini space probe by the Baltimore Peace Network. In 1997 due to concerns over the use of plutonium, other, spacecraft Cassini is visiting Saturn. A Euro children's stories explaining the Cassini mission, Yahoo group for the Cassini Huygens mission.